In this video, we will look at the molar solubility. So we have some ionic compounds like sodium chloride that completely dissolve in water, but we have some other ionic compounds that will not dissolve in water, or for like 100 grams, only a very small amount of those ionic compounds will dissolve in water, and the rest will remain solid. So for those types of ions, we use the equation shown here. As you can see, the equation has a double arrow. So if you have, just repeating, if you have a solid that is calcium fluoride, if you dissolve this solid in water, only a very small part of the solid is going to dissolve to give you the ions. Now, for this type of reaction, we have a constant that we call solubility product constant, KSP, because it is dealing with solubility. So KSP for such a reaction can be given by the products. So I have the concentration of products here. Don't forget the coefficient as to the power, divided by the concentration of reactants. But remember, in this case, our reactant, which is calcium fluoride, is a solid. So solids are not involved in equilibrium expressions. So that means KSP will be given by the concentration of the products only. So calcium fluoride is a solid. So solids are not included in equilibrium expressions. So we are going to solve a number of questions based on the KSP equation. So the equation about solubility. Now, let us define molar solubility. So what is this molar solubility? It is just a solubility in units of moles per liter. So what it means, we are just looking about how many moles of a substance dissolves in a liter. How many moles of a substance dissolve in a liter. So that is molar solubility. Now we'll look at a problem That will help us understand what this molar solubility is. Let us consider the dissolution of silver chloride. So the equation of silver chloride is given here. Most of the times you'll be given the equation, and the KSP of silver chloride is also given here. So it's solubility product constant, KSP. So the question is, calculate the molar solubility from the KSP. How do we solve this problem? The first part, you need to write the expression, the KSP expression. So based on this, KSP is given by the concentration of the product of the concentration of the product, Ag plus times Cl minus. But the KSP here is equal to 1.77 times 10 to the power 10. Now, if we look at the chemical equation above, if a certain amount of silver chloride dissolves, we'll say it will form X of the silver and X of the chloride ion, because this reaction is 1 to 1. So when you write a KSP expression like this one, you can substitute the concentration with X. So this one will be equal to X times X is equal to 1.77 times 10 to the power negative 10. This implies X squared is equal to 1.77 times 10 to the power negative 10. Therefore, X is equal to the square root of 1.77 times 10 to the power negative 10, which is 1.33 times 10.5 to the power negative 5 mole per liter. So that is the molar solubility of, so this is molar solubility of AgCl. That's how we calculate molar solubility when we are given a 1-to-1 equation like the one shown above. So let us look at another example. What is the molar solubility of lead 2 chloride in pure water? So the first thing is, sometimes you have to write an equation on your own, but here you are given the equation. So for this equation, when you dissolve a certain amount of lead chloride, you are going to form X of lead, because lead chloride and lead here is 1 to 1. But for this one, we have 2 in front here. So we also need to form, we need to form 2x. So don't forget that we have 2 in front, Therefore, we are forming 2x. So lead chloride is forming x moles of lead and 2x moles of chloride ions. So as usual, we'll start with KSP. KSP is given by the concentration of lead and the concentration of chloride, but to the power 2, because also of the coefficient here. So we substitute the x's in the concentrations here. So we have x for lead ion and 2x to the power 2 for the chloride ions. So when we multiply here, we have x times 4x squared, which gives us 4x cubed. So this one is equal to KSP. Now, the KSP of lead chloride is 1.43 times 10 to the power okay, where am I missing the KSP of lead chloride? Alright, let me just make a change for the KSP. I forgot to put it in there. So the KSP of lead chloride is 1.17 times 10 to the power negative 5. So this one, 4x cubed, is equal to 1.17 times 10 to the power negative 5. So we can say that x cubed is equal to 1.17 times 10 to the power negative 5 divided by 4. So I can continue it from here. X is equal to the cube root of 1.17 times 10 to the negative 5 divided by 4. So in that case, x is 1.43 times 10 to the power negative 2. So this is the solubility of lead to chloride. So those are the two simple examples of solubility, to calculating solubility given KSP. Now let's go on and look at another example. What is the molar solubility of silver sulfate in pure water? So in this case, we are given the molar solubility of silver sulfate. So we are calculating KSP when given the molar solubility. So we don't know the KSP now. So the question is saying the molar solubility of silver sulfate in pure water is S is equal to 1.4 times 10 to the power negative 2 molar. Calculate KSP. So the first thing you need to do to determine that question, so I'll say solution here. The first thing is you need to make an equation. So my equation will be silver sulfate in equilibrium with 2 silver aqueous and a sulfate ion, also aqueous. But KSP is given by the concentration of silver. Because there is a 2 here, you need to put squared, and the concentration of the sulfate. Now, if silver sulfate dissolves, it forms 2x here because of the 2 present here, and it forms X on this side. So what are we saying? X is the solubility. So if we substitute those x's here, we are going to have 2x and then times x. So this is 2x, but it should be squared times x, which makes again 4x cubed. But x is equal to solubility. So x is the solubility of a substance. So what it means is wherever there is x, you need to replace it by the solubility that we are given here. So the KSP is equal to 4 times 1.4 times 10 to the power negative 2, but this one is cube. So when you do the math, you find that the KSP is equal to 1.1 times 10 to the power negative 5. So the KSP of Ag2SO4 is equal to 1.1 times 10 to the power negative 5. That's how we determine the KSP when given molar solubility. Now let's look at another example. All right, I missed some example, but I'll just write it here. So which of the two compounds has a higher molar solubility. So we are given the two compounds. The compounds are as follows: Fe OH3 with a KSP of 2.8 times 10 to the power negative 39. This one versus zinc sulfate or zinc sulfide, that is zinc sulfide with a KSP of 3.0 times 10 to the power negative 23. So you look at this problem and say, all right, I am given KSP for these two reactions. Which of the two has a higher molar solubility? How do we deal with this? We need to calculate molar solubility for each one of the two compounds. So let us start with this one. So this one is our 1 and this one is our 2. So let's start with 1. The equation for 1 is given. So this is a solid, is equal to Fe 3 plus aqueous plus 3 OH, also aqueous. So we are saying that if FeOH dissolves, it will form an X here and it will form 3X on this one because we have 3 of them. And KSP is given by the concentration of ion and the concentration of OH, but to the power 3. What does this give us? And the KSP is 2.8 times 10 to the power 39. This one gives us X times, so I'll put this one in parentheses, times 3X to the power 3, which is 3X or 9X. So that is X times 3 squared is 27. So 27X cube. So finally we'll have 27X to the power 4 is equal to the KSP, which is 2.8 times 10 to the power 39. So continuing, X to the power 4 is equal to 2.8 times 10 to the power 39 divided by 27. So if we continue this side, X then is equal to the fourth root of 2.8 times 10 to the power 39 divided by 27. This that is fourth root, the fourth root of that. So this gives us 1.0 times 10 to the power negative 10 moles per liter. So that is the solubility. That is the solubility of ferric hydroxide. So now we have found the solubility of ferric hydroxide. Let's go on and determine the solubility of the zinc sulfide. So 2 for the zinc sulfide, our equation, solid aqueous also aqueous. So for this one, we know that the KSP is given as 3.0 times 10 to the power negative 23. So when zinc sulfide dissolves, here it will form X, here it will also form X, because it is a 1-to-1 reaction. So in this case, the KSP is given by the concentration of zinc ion and the concentration of the sulfide ion. Now by substitution, we'll have X times X, which is equal to X squared. So X squared is equal to our KSP, which is 3.0 times 10 to the power negative 23. And X is equal to the square root of 3.0 times 10 to the power negative 23, which gives us 5.5 times 10 to the power negative 12. So this is the solubility of zinc sulfate. So let's go to our question again. We are comparing two solubilities. We found that the solubility of FeOH3, which has a KSP of 2.8 times 10 to the power 39. So the solubility is equal to 1.0 times 10 to the power negative 10. And for zinc sulfate, which has KSP of 3.0 times 10 to the power 23. Solubility is 5.5 times 10 to the power negative 12. So based on this, FeOH 3 has higher solubility than zinc sulfate. But let's look at that. If you compare their KSP, you see that the KSP of ferric hydroxide is really high, while the KSP of zinc sulfate is low. So if you just look at the KSP, alright, let me say again, the KSP of ferric hydroxide is very small. You can see this is to the power negative 39. The KSP of zinc sulfide is higher. That is to the negative 23. If you just look at the KSP, you will think that maybe the zinc sulfide has higher solubility or dissolves more in water than the ferric hydroxide. But when you do the calculation yourself, you see that the ferric hydroxide has higher solubility than the zinc sulfide. That means the ferric hydroxide has a higher number of solubility than the zinc sulfide. So the zinc sulfide here is to the negative 12. The ferric hydroxide here is to the negative 10. So most of the time, do not rely on the KSP. If I ask you which one has higher solubility, you need to calculate like I have calculated here. Don't depend on the KSP to say this KSP is big, therefore this one has higher solubility. No. Most of the times it doesn't work like that. You need to do the actual calculation to determine between two compounds which one has higher solubility. So for the last question, I will make the next video for that. Thank you.